This is the 7th video on the course Computational Hydraulics. Last time we were talking about partial differential equations. So specifically we were focusing on elliptic forms of these partial differential equations. Among these elliptic forms, it can be expressed in terms of Laplace form or in terms of Poisson equation when there is a source or sink. So Laplace equation we do have in 2 dimensions is expressed as we have expressed last time with the second partial derivative of u, the variable u, along the x-axis plus the second partial derivative of u along the y-axis is equal to 0. So we can represent this equation in terms of finite difference approximations using the center difference method. So for balls along the x-axis and along the y-axis, which we have learned before. So representing nodes along the x-axis by I, nodes along the y-axis by j. So we can express second derivative of h, for example, if the variable is h, along the x-axis is equal to h at I plus 1's node along the j's axis minus twice of h at the i's node along the x-axis again, j is constant, plus h at the I minus 1's node over delta x square. And the case for second derivative of h along the y-axis is fixing x is going to be constant, in which case I is going to be constant. So h at j plus 1's node minus twice of h at the j's node plus h at the j minus 1's j minus 1 node over delta y square shall give us the second partial derivative of h along the y-axis. If you sum the two, then you can easily come up with this equation. And if we, for simplicity, if you assume delta x and delta y to be the same, then it will just give you the this Laplacian difference equation. So 5 nodes are involved here. So we typically call this 5-point equation, 5-point equation of Laplacian difference equation, basically. So the boundary condition, it may be specified as a constant figure, or it could be specified as a derivative. When it's expressed in terms of derivative, it's Newman's boundary condition. When it's specified as a constant, it's Dirichlet boundary condition. You may have also a combination of mixed boundary conditions of the Dirichlet and Newman boundary conditions. If the grid spacing is not the same, then obviously we can represent beta is equal to delta x over delta y, like we have expressed last time. Then the equation of the 5-point Laplacian equation would have these 4. So we have here represented -2 into 1 plus beta square to be gamma. Finally, if you just put delta x and delta y to be the same, this equation would reduce back to the 5-point Laplacian equation, the well-known 5-point Laplacian equation of these 4, basically. So once you said that, then you can use can just solve this simultaneously. As you can see, representations on the grid along the x-axis, I 1, 2, 3, 4, 5, and along the z-axis, along the y-axis, 1, 2, 3, 4, 5. So we are talking about values at the nodes, basically. Now let's look at how to solve this basic elliptic equation. You do have different ways of solving such linear algebraic equations. You may either use direct methods like Gauss elimination and Thomas algorithm methods. Very much common and easier, but it's susceptible to round-off errors. Whereas a very more robust technique is iterative techniques like Jacobi iteration, it could be, or Gauss-Seidel iteration, it could be, or SOR, or successive over relaxation techniques, or alternating direction implicit techniques are very known or well used types of iteration techniques for solving these linear algebraic equations. You may also use matrix inversion, very easier, yeah, or Cramer's rule if you wish, yeah, which are a little bit different variants of the direct method, I would say. Now, let's look at an example. Now here you do have a certain bar along the y-axis and along the x-axis. Temperatures are given. Those are basically boundary conditions. They are specified as constants. We are asked to find temperature at each of the interior nodes, basically. Now, as you can see clearly in the Lagrangian difference equation, we are trying to use 4 nodes surrounding a certain node I, j. So as you can see, it's essentially hi plus 1, first along the, talking about the x-axis, hi plus 1 and hi minus 1 along the x-axis, plus hj minus 1 plus hj plus 1 along the y-axis. So we are essentially summing all the surrounding nodes minus 4 times the interior node shall be equal to 0 as per if it is Laplace equation with delta x and delta y given to be constant or the same, actually the same. Then the Lagrangian difference equation is just summing the values at the surrounding nodes minus 4 times the interior nodes equal to 0, basically. So, expressing that set of equation for each one of these interior nodes, for example, for the first interior node, if we call that T1, the second interior node, T2, and the third one, T3, obviously, for the first interior node, then this shall be 0 plus T2 along the x-axis, plus 0 plus 0 along the y-axis, minus 4 times the center node, which is the T1, 4 times T1 shall be equal to 0. Doing the same equation for T2, you would have T1 plus T3 plus 0 plus 0 minus 4 times T2 is equal to 0. Doing similarly for T3, you do have T2 plus the value at the boundary condition, which is 100, plus 0 plus 0 minus 4 times T3 is equal to 0, basically. You can rearrange this set of equations, basically, to have the same terms on one column, yeah? Then you can turn this into a simultaneous equation. Basically, the first equation is like 4 times T1 plus 1 times T2 plus 0 times T3 is equal to 0, basically. And the second equation could read 1 times T1 plus negative 4 times T2 plus 1 times T3 is equal to 0. And the third equation is 0 times T1 plus 1 times T2 plus negative 4 times T3 is equal to negative 100, basically, just rearranging the equations. So ultimately, you would come up with this set of equations and then representing the coefficients matrix by A, the values of the unknowns T1, T2, T3 by X, and the right-hand side by B matrix. Now we are supposed to find out matrix X, which is A times X is equal to matrix B, vector B, you can say. And obviously, x is equal to A inverse times B. Now, let's solve this set of equations in Excel. So you can see it here. Matrix A is negative 4, 1, 0, 1, negative 4, 1, 0, 1, 4. That's matrix A. Matrix X is not known, but A times X is equal to matrix B, basically. As you know, two matrices could be multiplied only and only if the column number of the first matrix matches with the row number of the second matrix. So A and X could be multiplied only when matrix A obviously is 3 by 3. Number of rows is 3, number of columns is 3. Whereas matrix X is 3 by 1. 3 rows and 1 column. So 3 by 3 times 3 by 1 is 3 by 1, obviously. So B shall be 3 by 1. Obviously it is. Now, to find X, we have said we need to find A inverse times B. So we need to find A inverse. Obviously, a matrix can have an inverse only when it is a square matrix. But being a square matrix doesn't guarantee that it would have an inverse. It could be a singular matrix. So anyway, if it is a square matrix, then its corresponding inverse is going to be square again. So let's choose 3 by 3 space, and then is equal to, we say, in Excel, M inverse, we say. Then we open the bracket, and then choose matrix A, then close the bracket, and then we have to say Control Shift Enter. Once we have found A inverse, we need to multiply A inverse by B. A inverse is 3 by 3. B is 3 by 1. 3 by 3 times 3 by 1 is going to be 3 by 1. So I'm going to choose 3 by 1 space. Then is equal to M mod A inverse, comma, B. Then Control Shift Enter. Then that should give you the values of X, obviously. So T1, T2, T3 are obviously found to be these values here. So obviously T1 is 1.786, T2 is 7.143, and T3 is 26.79. So we have found this set of equations for the Laplace equation. Mind you, here the assumption is delta x and delta y are the same. But if they are different, then you have to rely on this set of equations. Or you can just expand and try to find the set of equations yourself. That's not difficult as such. Now, what about if it is a Poisson equation? In which case, second derivative of u at x plus second derivative of u at y is equal to something. In this case, equal to -4. So we are given here with a closed boundary curve, which is essentially a square bounded by straight lines. So from -2 up to +2, with mesh size of 1, 1 means -2, -1, 0, 0, 1, 2. Those are the values of x. And the values of y is similarly -2, -1, 0, 1, 2 at mesh size of 1. Since delta x and delta y are the same, we can just come up with the same set of equations with the Laplacian, except that this time is going to be equal to -4. Yeah? So we are asked to obtain a finite difference solution. Obviously, in elliptical equations, there is no time. Yeah, there is no time. So we are supposed to give here boundary conditions, no initial conditions, but boundary conditions. So the boundary conditions are given along the 4 axes. So we're going to solve this set of equations. This is Poisson type of equation, obviously. So you can see here, these are the nodes here. So we are at -2. If you just look at this graph here, in naming the nodes, I've tried to use along the x-axis values of I. So it would just start from the first, second, the third, the fourth, the fifth. Along the y-axis also starts from 1, 2, 3, 4, 5. So the point where the lines intersect would form the nodes, obviously. So the names of the nodes are given there. So we are given that we are going to find at each one of those nodes. So the first node along the x-axis starts from -2, -2, -1, 0, 1, 2. For the y-axis also, at the left bottom corner, we have assumed to be the starting point where x and y meet. So there it starts with -2. And then the second one is -1, and then 0, then 1, 2, obviously. So assuming the similar constant size of delta x and delta y, so we are going to use that set of equations expressed here is equal to -4. So for the first equation, this would read, similarly from the Laplacian difference equation, this would read the value. We are going to add all the values at the surrounding nodes, minus 4 times all the surrounding nodes, minus 4 times the interior node is equal to -4. So this would look like here at the boundary condition, it's going to be 0, 0, obviously. Yeah, at the boundaries is going to be, it's given to be 0, u is equal to 0 on the boundaries. Yeah. So using that value here, we can find for node P22 or U22, in this specific case, shall be equal to what? 0 plus U32 plus U23 plus 0 minus 4 times U22 is equal to -4. Then for node 23, surrounding nodes, is going to be 0 plus 33, U33 you can say, plus U24 plus U22 minus 4 times U23. Similarly, doing for U24, it's like 0 plus U34 plus U23 plus 0 minus 4 times U24 is equal to -4. So doing similarly for each one of those 9 nodes, you do have this set of equations. Now, rearranging terms, then you'd have this form of the linear expression of the equations. Now, obviously, these are the values here. These are the corresponding coefficients for each one of those nodes here. Yeah. So Corresponding to U22, the coefficient is 1 here. From the first equation, it's -4 here. Yeah. Corresponding to U23, the coefficient is 1. Corresponding to U24, there is no coefficient there. Corresponding to U32, it's involved there, so it's 1. 33 is not involved, so it's 0. 34 is not involved, it's 0. 42 is not involved, 0. 43 is not involved, 0. 44 is not involved, 0. Yeah, so these are the coefficients pertaining to each one of these variables. So from those set of equations, we just identify the coefficients here. And the right-hand side, in each one of them, it's -4. So we are supposed to find out the coefficients for U22, the values for U22, 23, 24, 32, 33, 34, 42, 43, 44. So all you have to do is, you have to find out the inverse. Yeah. First, you need to find out the inverse as we did earlier. So we just found here the inverse. Yeah. So that's the inverse, M inverse, of the one with the coefficients. Once you find out the inverse, then we are going to multiply with the inverse this -4, this set of equations. So that should for the values here. Huh? So this is 9 by 9. 9 by 9 times 9 by 1 is 9 by 1. So is equal to M amount of the bracket. Then let's go for the inverse here, comma. Then matrix O, vector O, 14 up to O, O14 up to O22, basically. So we have just chosen the two matrices to be multiplied, and then we have to say Control Shift Enter. So that should give us the values for each one of those nodes. So basically, the values at each one of those nodes is given here. Huh? So you can see it here, corresponding to U32, it's U22, it's 2.75. Corresponding to U23, it's 3.5. Corresponding to U24 is going to be 2.75. Corresponding to U32, 3.5, just goes on. So we have just found the values at each one of those nodes for Poisson case. Now let's move to parabolic equations. Parabolic equations, in which case b squared minus 4ac is equal to 0. So if you consider heat conduction equation, for example, is a diffusion problem with K defined as diffusion coefficient. Here, time is involved. One spatial scale and one temporal scale for one-dimensional diffusion equation. Now we can substitute each one of those differential equations, partial derivatives, by the finite difference equivalence. Here there is time, so for time we are going to represent by n. For the one spatial scale by I. If there had been another spatial scale, then we would have represented that by j actually. Now, there are several possibilities for representing the partial derivatives. You may either express the spatial partial derivatives in terms of the variables at the known time level, which is n is a known time level. Then we express the equation like explicit finite difference. But if we express the spatial partial derivatives in terms of the variables at the unknown time level, mind you, the spatial derivatives, in terms of the unknown time level, which is n plus 1, then we call the representation, the finite difference, implicit finite difference scheme. Now, you may have representations. F here is going to represent forward, B is backward difference, T is time, S is the space. So when you have a scheme of FTBS, it's forward time, backward space. When you have got BTBS, which is backward time, backward space. If it is FTCS, then it's forward time, centered space. CTCS is centered time and centered space. Now, although you have different possibilities to represent your finite difference, we have to look for a scheme which is consistent, stable, and convergent to the analytical solutions. Quite often, backward schemes are also referred as backward spatial. Spatially backward representations in finite difference are typically called upwind schemes. Similarly, the spatially centered schemes are called centered schemes, basically. So you can represent this representation of the parabolic equations using many different ways. Among others, you can represent using forward time centered space, FTCS, forward time and centered space. Now, we can use for the time, the temporal partial derivative, we can use forward time here, obviously. And n would tell you the time, and the j would tell you here the space. So we are trying to use in the forward time between the n's temporal time, n's node, and n plus 1's node. You have tried to express the forward difference in terms of temporal time, temporal scale. Whereas in terms of the spatial scale, we are going to represent the second partial derivative using center difference. So while at I, j, sorry for the misleading representation there in the figure, and here in the figure it's j, but there it's I. So I'm going to use I from now onwards, actually. So centered at I, n, spatially, we're going to use the second partial derivatives using centered scale. So that's going to be like Tn at i's plus 1's node plus Tn at I minus 1's node minus twice of T at the i's node, actually. This is done at the current time, which is n, basically. So you can see, if you just rearrange terms there, representing by k, the diffusion coefficient, times the spatial temporal scale, delta t, over delta x squared by lambda. Lambda here is the diffusion Courant number. I will soon express what Courant number means. But for the time being, you can just take it as it's a Courant number, but specific to diffusion problem here, lambda. Because for hyperbolic equations, it's a bit different. So lambda here. So representing k times delta t over delta x squared by lambda, then you have that equation for t at the i's spatial scale and at the n plus 1 temporal scale. You can express it like that. As you can see, what's important in that equation the terms which are involved in that equation to find Ti at n plus 1's temporal scale are Tn at the i's node, Tn at the I plus 1's node, and Tn at the I minus 1 node. So using those 4 nodes, known nodes, we are going to find out Ti at the n plus 1's node. Obviously, you can see the stencil, the finite difference stencil, or from that equation, what is given, which nodes are given, and what is required from the stencil. You can clearly see that. So what we are looking for is the unknown time scale, using known time scale. So this scheme, since all the partial derivatives are expressed at the known temporal time scale n, then we say this equation or this scheme is explicit scheme. Now, we can solve this equation. We are asked to solve the following partial differential equation by the explicit finite difference method. Boundary conditions are given here. The value of the temperature for any time at x equal to 0 is 0. And at x equal to 1, for any time t greater than or equal to 0 is going to be 0. And the initial condition is given as t is equal to 2x at t is equal to 0, at t is equal to that initial condition, if the time is involved. So at t is equal to 0, for temporal scale from 0 to 0.5 up to 0.5, it's increasing with a slope of 2. And then from 0.5 up to 1 is going to decrease with a negative of same magnitude slope, with negative 2 slope. It's going to decrease. So I have just plotted that initial condition. On the slide you can see that's the initial condition. So we are asked to solve the problem for time increments of 0.001 and at spatial distance of at delta x of 0.1. We are asked to solve the problem. What's the value of t at different spatial distances and at different temporal times? Now we are going to solve this problem. So here you can see the equation here. Explicit scheme, delta t is 0.001, delta x is 0.1. So lambda, which is k times delta t over delta x squared, k is 1 here. So lambda is going to be 0.001 over 0.1 square, which is essentially 0.1 lambda. So here the x-axis is given, the y-axis that's for the time, yeah. So at x equals 0, it's going to be 0, and at x equal to 1, it's going to be 0 again, yeah. So just for simplicity, I'm going to do it downwards, temporal scale. So I being the first node, second node, third node. So we have divided the spatial scale at each one of them at 0.1, 0.1 nodes, 0.1, 0.1 spatial scale until x equal to 1. So initially it was 0, then 0.1, 0.2. It just kept on increasing by 0.1, and then finally it's 1. For the temporal scale, we started with 0, then we just kept on increasing by 0.001. Yeah, so you do have the increment in time. Now, using this set of equation for the explicit forward time, center space scheme, yeah, using this scheme, we're going to solve that using FTCS. So using FTCS, we are going to use this set of equations. So we're going to use this equation. You can just, for easy reference, we have just popped it here. Yeah. So now we can solve the value from the initial condition at t is equal to 0. We can find the corresponding values of the temperature at each one of the spatial nodes. Kept on increasing until delta x goes to 0.5, and then it kept on decreasing until x is 1, kept on decreasing. But it's symmetrical, as you can see it, yeah, obviously from the graph. Now, for the rest of the equations, we're going to calculate ourselves. Yeah. So let's solve for the first node here. Essentially, for this node means I is 2 and t is 2. Now, using this set of equations here, provided here, remember, we're going to find for n plus 1's time, mind you, for this node specifically, for this specific node, I is 2 and n is 2. Yeah. And then this equation would give you a result for t at i's node and at n plus 1's time. So obviously here, n plus 1 is going to be 2, and I is going to be 2 again. Since n plus 1 is 2, obviously n is 1. So for that specific node, in that segment, n plus 1 is going to be 2, and I is going to be 2. So n from that is 1, and I is 2. So here, t and I means n is 1, obviously. I is 2. So for the first spatial, the second spatial, using the second spatial node, and the first temporal time, so the first temporal time and the second spatial node means this node, basically. This one, I don't know if it's visible for you. This one, yeah, that is t and I. Yeah, well here, this one is t and I, plus t and I plus 1 is while on the nth time axis, along this axis, while along this axis, we are looking for the I plus 1's spatial scale, which is this one, 0.4. 2 and I is basically this node. 2 and I minus 1 is this node. Yeah. So using this set of equations, you can easily calculate here t and I, which is the value here, plus lambda times the value on this side plus the value surrounding points minus twice of at t and I. Yeah. So lambda is constant. We just finished that. So using this set of equations, now you can just populate. Yeah. So we have just found for all the values now, obviously. Yeah. So it's very simple. Huh? Once you do it for one point, you just populate that in Excel. So we have just found for different time and for different spatial scales the corresponding values of values here. You can just plot this if you wish. Yeah. So we just use the explicit scheme and then we have tried to find out the values. Mind you, here we have used a value of lambda as equal to 0.1. You are required to change at least delta t so that the value of lambda is equal to 0.5 or above, and look the consequence, how things would change. Here everything is positive now. The minute you change this one, yeah. So if you just multiply this by 6, by 5, let me see here, lambda is 0.5. That's still okay. Yeah, it's symmetrical, and the maximum lies somewhere in the middle, still, in the middle. But the minute you change that one, instead of 0.7 to 0.9, for example, then you start to see negative values now. Yeah, the result is unstable. It's going to be unstable, and it's unrealistic in that case. Yeah, so the value of lambda here, as you can see, it's more than 0.5. Yeah, so we'll talk about instability problems in explicit forms of parabolic equations. Yeah, instability problems when the value of lambda exceeds 0.5. So this was explicit scheme, remember? Yeah. So explicit schemes have problems relating to stability. But implicit methods would overcome these problems by introducing more complicated algorithms. Typically, you need to develop simultaneous equations. For example, in case of explicit schemes, in the grid point involved with the spatial difference at the known temporal scale, then we are supposed to find out the grid point involved in the time difference at the unknown time. The unknown time is going to be expressed using known times in the explicit scheme. So using n, you're supposed to find n plus 1 here. But in case of implicit schemes, in the spatial derivatives, you can see you're going to find out the values at the n plus 1 node using the values at the unknown temporal scale. So it requires to develop a set of simultaneous equations. Implicit method. So the same set of equations, what is changed this time is instead of using here n in the spatial derivatives, you're going to put that n plus 1 at the unknown time. The spatial derivative is expressed at the unknown time. Now representing lambda, the diffusion Courant number, which is k times delta t over delta x squared by lambda, and then just expressing the term, you'd have that equation now. Now, expressing the values at the boundaries, let's say at the initial point, yeah, and then substitute that in the set of equation. And for the last interior node, at the beginning node and at the ending node, yeah, if you express that, then you would have a system of equations which is usually tridiagonal. When it is tridiagonal, basically it would have lots of zeros in the matrix, so solving that equation would be very much easier, those set of simultaneous equations. But typically, instead of using this implicit scheme as it is, we typically employ other schemes which are an alternative to the implicit scheme, like Crank-Nicolson scheme. In case of the Crank-Nicolson scheme, it tries to average the spatial derivatives using explicit scheme, which is at the nth time node, and the spatial derivatives at the n plus 1's node using the implicit scheme. So it's essentially an average, half of the implicit scheme and the explicit scheme. And then we are going to use, similarly, we are going to insert boundary conditions into this set of equations to solve the partial differential equations. Now, let's look at an example. But before I move to the example, remember, when we are dealing with explicit schemes, we have noticed that it's stable and convergent when the value of lambda is less than or equal to half. Yeah? So let's look at the same problem using Crank-Nicolson scheme. Same problem here, using Crank-Nicolson scheme. So in the Crank-Nicolson scheme, we have tried to use, which is the average of both explicit and implicit schemes, and then we have tried to find out this set of equations. But this time around, we are going to use the value of k is still 1. We have just reduced the value of delta t. Earlier, the value of delta t here is 0.001. Special distance is 0.1. But we are going to increase the value of delta t. So in doing so, lambda is going to be increased. Implicit schemes have no problems with stability as such, as much as explicit schemes do. So here, we are trying to express delta t as 0.01, not 0.001, but 0.01, yeah, at coarser temporal scale. So lambda is found to be now just 1. Yeah. So when you make lambda is equal to 1, then things would be pretty easier to calculate, isn't it? Yeah. So we're going to calculate at lambda is equal to 1. So on this set of equations, instead of lambda, we just insert 1. So ti minus 1, n plus 1, plus lambda is 1. So 1 plus 1 is 2, 2 times 2 is 4. So you do have this set of equations now here. And on the right side, 2 into 1 minus lambda, lambda is 1, so 1 minus 1 is 0, so that term would cancel out. So you do have this set of equations now, ultimately. The last equation now. Now, using the last equation which we have derived, for every time scale, let's say for the first time scale of 1, and for all the spatial scales starting from the second node up to the 10th one, because for all the left side at x equals to 0, the value of t is 0, obviously. And at x equal to 1, the value of t is 0 again. That's already given. At the boundary condition, it's going to be, it's given to be here, t is equal to 0 at x equal to 0. And at x is equal to 1, its t is going to be 0 here. Then in the initial boundary condition, it's the same as the one which is expressed earlier, which is it keeps on increasing until x equals to 0.5. It keeps on increasing. Yeah, it's 0.2, 0.4, 0.68, 1, and then it keeps on decreasing. That's the initial condition. Yeah. So the values in the gray, they are already given. So we're going to find out for the others now. Now for the first, for n is equal to 2, for n is equal to 1, yeah. But for I is equal to 2, yeah. For I is equal to 2 up to 10, we are going to compute the set of equations now. Yeah, n is 1. Yeah, n is 1. But I goes from 2 to 10. Yeah, because at I is equal to 1 and I is equal to 11, they are given already, they are known. Huh? So using this set of equations now, we can just put here in that equation which we have when substituting lambda is equal to 1 with the equation which we have come up with, we are going to find values. Obviously, t for the first node and for any time at t1n. When I say t1n, the 1 would represent the spatial scale and the n would represent the temporal scale, obviously. So the first subscript is the spatial scale and the second subscript is the temporal scale. So 1n is always 0, obviously. Yeah? So, and 11n is also 0, we know that. So we start with for n is equal to 1. For n is equal to 1 and I is equal to 2, yeah, then plug it in that equation. When n is 1, the equation would read like negative t at n plus 1, which is 2, I minus 1, which is 1. So negative t 1, 2, plus 4 times t I, which is 2, n plus 1, which is 2 again, because n is 1, and 1 plus 1 is 2. So 4 times t, 22, minus t of I plus 1, I is 2, remember, so 2 plus 1 is 3, n is 1, 1 plus 1 is 2, so t is 3, 2, sorry, is equal to t of I is 2, so 2 minus 1 is 1, t 1, 1, and n is 1, plus t of I plus 1, I is 2, so 2 plus 1 is 3, n is 1, so t is 3, 1. So we just found for the first line. Since it's going to be symmetric from the 6th node onwards, we're going to calculate from I is equal to 2 up to the 6th node. From that onwards, it's going to repeat itself. Yeah? So we are going to T52 is essentially T72, obviously. T52, the 5th node, spatial node, and the second temporal time. At the second temporal time, the 5th node and the 7th node would have the same magnitude. Basically, T51 along the first temporal time scale, the 5th node and the 7th would have the same. They are symmetric. Yeah. So we are going to solve this for the first equation up to the 6th node. We just finished that. Then we are going to do it for the I is equal to 3. Yeah? And then I is equal to 4. I is equal to 5. Just keep on doing that up to I is equal to 6. Yeah? Obviously, in this set of equations, what you have to change is only the value of I. N is going to be 1. Huh? So once you have the first equation, the second equation, just changing. Keep on increasing I from where it is. Initially it was negative t 1, 2, and then it's negative t 2, 2. Then negative t 3, 2, negative t 4, 2, negative t 5, 2. Then plus 4 times t 22. I was 2. Subsequently 4 times t 3, 2, 4 times t 4, 2, 4 times t 5, 2, and 4 times t 6, 2. So you have the 6, the 5 equations now. Now let's plug in the values, the known values. T12, by definition, it's the value at the boundaries. Yeah, that's 0, obviously. Plus 4 times T22 minus T32, and T11 is 0, obviously. Value at the boundary. T31 from the initial condition is given to be here 0.4. Similarly, for the second set of equations, negative T22 plus 4 times T32 minus T42 plus is equal to T21 initial condition is 0.2. Yeah? And T41 initial condition 0.6. T31 initial condition 0.4. T51 initial condition 0.8. T41 initial condition 0.6, and T61 initial condition, which is 1. And T51 is 0.8, T71, it's symmetry, that's also 0.8. T52 and T72 are equal, we know that. So we just add them to be like twice of T52. So you do have this set of simultaneous equations. Now let's solve. Now let's rearrange the terms like we did with the elliptical equation. We just keep the coefficients here, and then the right-hand side values on this side. Then here, then you are able to calculate what? It's like at one go, you could have done this thing, yeah? Just multiplication of the inverse of these coefficients times the right-hand side vector, yeah? So that should give you the values right away. Yeah. So we have just obtained the values for T22, T32, T42, T52, T62, obviously. Now, similarly doing for n is equal to 2 for each one of these partial scales from the second up to the sixth, similarly. And remember the symmetricity. And then you can find the second set of equations. And then solving that simultaneously, that should give you the value of T23, T33, T43, T53, T63. Once you obtain these values, just keep on doing it for n is equal to 3, n is equal to 4. You just keep on doing that. Then it should give you here the corresponding values now. So this is the first value for T22, then T32, yeah. I just inserted that just to read it automatically. I just made it better. And obviously the values here, that is the symmetric value here. So using that, we just finished this. So ultimately, you would have such a figure here. So the initial condition is this color here. As time goes on, the temperature keeps on cooling down and down and down as time goes on. Huh? So this is the implicit form, or using Crank-Nicolson scheme, we have tried to solve this equation. Mind you, how about if you change here the value of delta t here? Does it bring any change? Let's make 0.01 instead of 0.01. Let's make it 0.002. We don't see here any significant change, essentially. Yeah. If you decrease that instead of 0.01, yeah, I could have made that 0.5. Yeah, not significant change as such, not change. So here, yeah, no change as such. Yeah, in the implicit scheme or using the Crank-Nicolson scheme. So you can see here, relatively, as delta x and delta t approach to 0, if the results of the numerical scheme approach to the true solution, then we say it has got convergence. If at any stage of the computation, the errors keep on minimizing, yeah, or attenuated, then we say we have achieved stability if the errors do not amplify as the computation progresses. Yeah, explicit methods would be stable and convergent for values of lambda less than or equal to half. We are going to prove this in the next chapter. Now let's talk about finite difference using hyperbolic equations. Basically, hyperbolic equations, here we talk about hyperbolic equations of first order. You can also talk about hyperbolic equations of second order, but due to its very common use and as of application, we are going to focus on hyperbolic equations of first order. So here we talk about the pure advection equation. The pure advection equation would have the first partial derivative of u at t plus a times partial derivative of u at x is equal to 0. So this is a pure advection equation. So if you're talking about certain wave, so A would tell you the celerity due to the analytical solution. So it's assumed to be constant and positive. So in order to solve this hyperbolic equation, which is a pure advective equation, you can have a number of different schemes depending on the approximation of the derivatives. You can assume the partial derivative of u at t using finite difference method, forward finite difference method, backward finite difference method, or center finite difference method. You can assume the first derivative of u at x using forward difference, using backward difference, using center difference. So any combination of them would produce a number of different types of schemes. Now, let's look at one of these schemes, which is an explicit scheme. So we are going to focus on the forward time and backward space scheme, which is an explicit scheme, FTBS. So the temporal derivative is going to be explained using the forward time, and the spatial derivatives is going to be expressed using backward space. And here, CR, Courant number, is explained as A over delta x over delta t. Obviously, A is the celerity of the analytical solution, whereas delta x over delta t is the celerity of the numerical solution. In method of characteristics, remember, we have tried to find out dx per dt. That is the slope of the characteristics direction. So that is the celerity of the numerical solution. So the celerity of the analytical solution over the celerity of the numerical solution shall give us the Courant number. So Courant number is equal to celerity times delta t over delta x. So that gives you the Courant number. So if you just plug those finite difference representations using forward time and backward space into the advection equation and represent Courant number by A delta t over delta x, that should give you u at the j's spatial scale and n plus 1's temporal scale is equal to Courant number times u at the j minus 1 spatial scale and the n temporal scale plus 1 minus Courant number u at the j's spatial scale and n temporal scale. As you can see, we are going to find the value at the unknown time using the values at the known time. So this is essentially an explicit scheme. You can see the stencil of the finite difference scheme here using values at j and j minus 1 of temporal time n. At those 2 points, we have tried to find out the value at the n plus 1's time, but at the j's spatial scale. So you can see the stencil of the finite difference scheme here. This is an explicit scheme. Now we'll talk about its convergence and the stability in the next chapter. Essentially, you can see in this advection scheme, when the current number is equal to 1, then this equation would show you ujn plus 1 is equal to uj minus 1n, which is the magnitude and shape of the variable won't change. It just only traverses from one spatial scale to the next spatial scale for at different points of time. It just traverses between two different points, but it would just maintain the shape and the size. Yeah. So this is very much true in the FTBS schema. So it just maintains the shape. This is very much true in kinematic wave routing, isn't it? Now, you can also express the pure advection equation using backward time and backward space. In which case, the backward time, remember, using values at this is backward time and backward space. So using the n plus 1's time and using the n's time. Yeah. Backward time. Using n and n minus 1, you can just make it, yeah, backward time, obviously. Or n plus 1 and n, obviously, backward time. Yeah? So it's going to be like the n is, the value at the n is temporal time, minus the value at the value at n minus 1, or the value at n plus 1, minus the value at the n's time. Yeah? So that's going to be like backward time. Yeah? And using backward space, just rearranging terms a little bit, expressing current number as usual is equal to a over a times delta t over delta x. Yeah? Shall give you this representation of the backward time and backward spatial scale. As you can see it here, the spatial derivative is expressed using backward space. So this is basically upwind scheme. And since it's expressed in terms of n plus 1, yeah, using n plus 1's at n plus 1's node, spatial scale at n plus 1's node, then we shall say this scheme is implicit. Yeah? But unlike the first equation here, when current number is equal to 1, it doesn't reduce to uj n plus 1 is equal to uj minus 1 n. No, it's not. Yeah, it's a bit different this time around. Yeah, so we can talk about, to be specific, it's going to be like at uj at n plus 1's time, it's going to be the average of uj at n plus uj minus 1 at n plus 1. It's going to be the average of the two for the backward time and backward space, actually, when the current number is 1. Now, we can also represent it using the pure advection equation that could also be expressed using forward time and center space. So obviously, it shall give you here, and then rearranging a little bit, with current number, as usual, is equal to a times delta t over delta x. It's going to be u of the j's spatial scale and n plus 1 temporal scale is equal to u j at n temporal scale minus half of current number times u j plus 1 spatial scale at n temporal scale minus u j minus 1 n. When Courant number is equal to 1, then that would read like unj minus unj plus 1 minus unj minus 1 over 2, obviously. But this scheme is unconditionally unstable. You can easily prove that. So it's not very often used. Only for the very first time steps you may easily employ because of its simplicity, but cannot use it for all the time, basically. The other one is the centered time and centered space. So we call it centered scheme, basically. So both temporal derivative and spatial derivatives are explained using center difference of the first derivatives. So you do have ujn plus 1 is equal to ujn minus 1 minus Courant number times unj plus 1 minus unj minus 1. So basically when the Courant number is 1, basically un plus 1j is equal to un minus 1j minus unj plus 1 minus unj minus 1. So this scheme would have this problem. It may produce two solutions for the same problem under special boundary conditions. Now, the other way of representing the pure advection equation, you can also employ the very common scheme, which is the Preissmann scheme. It's actually a 4-point implicit scheme. 2 points are going to be taken in space and 2 levels in time. So you do have 4 nodes. But the derivatives are not approximated at the nodes of the grid, but somewhere inside the grid. So if this node, let's say P, is somewhere at a point along the temporal scale, theta times delta t, or somewhere along the x-axis, psi of delta t from the i's node, then you can find the weighted partial derivatives for each of the temporal derivatives and the spatial derivatives using the Preissmann scheme. And the Preissmann is a French scientist. The box scheme, that's the one which is developed from USA, but of course the Preissmann scheme is very well known and the one which has discovered the scheme. Now, if you consider a grid which is equally spaced in space and time, so for a point P located between points I minus 1 and I in space, and time levels of n and n plus 1, you can express the temporal derivatives as weighted average of temporal derivatives at the j minus 1 node and temporal derivatives at the j's node. Basically, you're using forward difference in both cases. It's the weighted average of the forward difference of the temporal derivatives at j minus 1 node and j's node. So the weight here is psi. Whereas for the spatial derivatives at the p's node, again, is going to be the weighted average of the forward difference of the first derivatives at the n plus 1's time and at the n's time. So when you are trying to calculate for the spatial derivatives, here We are going to do it at j and j minus 1, between j and j minus 1, but for different times, weighted average of the different times at the n plus 1 and at the nth node, at the n plus 1's time and the nth time. Whereas for the temporal derivatives, it's going to be calculated at j minus 1 and j again, j minus 1 and j again, yeah. But since it's temporal derivatives at the n plus 1 and n time, so it's going to be weighted. Whereas for the temporal derivative, the weight is going to be psi, and for the spatial derivative, the weight is going to be theta. So these weights are going to range from 0 to 1. So if you just plug those two equations into the pure advection equation, and then try to rearrange terms, yeah, then you can find uj at the n plus 1's time is going to be like aj times uj minus 1 at the nth time plus bj times uj at the nth time plus cj, uj minus 1 at the n plus 1's time. The coefficients aj, bj, and cj, they are expressed at the bottom of the slide here. So the scheme is explicit when theta is equal to 0. When theta is equal to 1, it's going to be fully implicit. If the value of theta is less than 0.5, it's going to be fully unstable for the Preissmann scheme. By the way, Preissmann scheme is very much widely used. Maybe in the second order form, you can find it in Hecras, for example. In Hecras model, it uses the Preissmann scheme basically. Yeah. The Abbott-Ionescu scheme is used in the Mike 11, whereas the Preissmann scheme is used in Hecras. So we have tried to express this using the very well-known Preissmann scheme. So next time we're going to compare the convergence, consistency, and stability of some of the schemes which we have explained here. So for now, at the end of the lecture today, next time we'll talk about new chapter on properties of numerical methods.